Hello, guys. My name is Jonas Bonér. I'm the CTO and founder of Akka, formerly called Lightbend. I started the company in 2009, and we incorporated as sort of an entity with a US-based headquarters in 2011. So I've been at this for about 15 years, but it's all started around Akka that I started in 2009. And I assume we're going to talk a little bit about it in this podcast. So I'm based in Sweden, and there's a lot more to say, but I'll leave it at that.
Okay. Hello, guys. My name is Łukasz Marchewka. I'm a software and solution architect. I have played with distributed systems a lot in the past. Now I play a role of Scalac CTO. I have a lot of topics, question about distributed system, how to implement and use it correctly. And so welcome on the CTO Ask CTO podcast. So let's start. We are going to talk about distributed systems, but can you explain what is distributed system?
So there's of course a lot of definitions out there, but a useful one, the way I see it is that a distributed systems is simply sort of a collection of independent computers that are separated by the network, which is an important one. That in some way tries to work together as a single cohesive system to achieve some sort of goal, providing value for the user or whatever it is. But if often when I talk about distributed systems, I sort of do the inverse, and I look at what are they sort of the two main key challenges to distributed systems, and that is sort of the way I break it down is in the most simplistic ways is that it's essentially two different challenges. You have to try to overcome that information as latency. That leads you to a lot of problems to overcome, or challenges rather than problems. And if we look at it in a more positive light, challenges around consistency, how you deal with convergence of data, how you manage time, because time can't be absolute and sort of globally consistent. And the second thing is that the independent things fail independently, and you have since the distributed systems, it's really sort of the composition of independent things. Since they can fail independently, that can lead you to what is usually called partial failures, and that can be very hard to manage in a way. So I don't know if that's a good definition, but that's a little bit how I see it.
Yes, I think it's quite difficult to explain what is distributed systems. And nowadays, I think almost everything, each new system is just distributed. But maybe can you see two different implementation or architecture, the better one, which work very well in distributed world, versus something what is still distributed systems, but has a lot of different kind of problems. Can we, for example, distributed system also can use one centralized database? What shouldn't probably, or where each service has own database, or for example, is the easiest example.
Yeah, I mean, there's a lot of, most people that's been around for a while, or come from a world where we built monoliths, where you have sort of a classic 3-tier architecture with a single database at the bottom, and back in the world where we didn't have distributed systems, but the solution was essentially to scale up, meaning adding more processing power. It was really the only means to meet higher demand on the application. Then that was a reasonable thing to do. But today with distributed systems, it's usually incurs a ton of problems, because you will end up with a single point of failure. If you only have one single database, you will end up with a single point of bottleneck, where you can bottleneck on IO and the connection pool and so on. And a better solution is often then to use, sort of data partitioning and to try to shard your data across more than one thing, so to speak, to avoid these type of things. A lot of the problems, I think, come from sort of bringing over old tools and old ways of thinking, old designs into this new world of distributed systems, and expect things to work, because it usually doesn't. It only sets you up for failure, and it's really requires a completely different mindset and a different design and architecture from ground up. Which is often quite challenging. You have, of course, a learning and an unlearning, problem here. You have to sort of unlearn and reset and look at what distributed systems actually embody and require from first principles. And it's better now, but 10 years ago, when the cloud started to emerge, it was a lot of failed cloud projects because of the sort of mismatch between sort of old ways of doing things and this new world that is a lot less forgiving in a way. Yeah.
So what part of distributed system is the most important to be successful?
Yeah, I think it's embracing the network, understanding that the network is there. You have the 8 fallacies of distributed computing. It starts with this classic Peter Deutsch sort of write up, that it starts with the network is reliable. It's really inherently unreliable, and I think a lot of the problems come from assuming that the network is reliable, that a remote call is similar to a local call and has the same guarantees, which is but when you put the network in between, to two communicating parties, A and B, then anything can happen. Messages can get dropped, they can get garbled, they can be duplicated. If there's retransmissions that has to be made and so on. So there's a lot of, I think most of the problems come from not understanding that the network sort of completely changes the picture, and the best way to get around this, in my view, and what Akka's really been embodying is to fully embrace the network, and having network so the constraints of the network, so to speak, first class in the programming model. So you have actually means to manage it, because if you try to sort of masquerade it up, and shield the developer from the fact that you're working in a world where everything can go wrong, when there's uncertainty and so on, then it can really be, what looks like a beautiful abstraction can really becomes a leaky abstraction that leaks so much that it fails to be useful, because if you don't have constraints under your fingers and have a way to manage failure and have a way to manage uncertainty, then and instead are faced with sort of a shiny black box, then it's really, really hard to build reliable systems. That said, if of course the programming model or tools or whatever, they should not expose more complexity that is absolutely needed. But network and uncertainty and the risk for failure, they're also inherent. So they are really part of what I call the inherent complexity of the problem space. And I think that has to be first class, so you have a way to actually manage it in the application.
You have surprised me, because I thought you would just answer data, but I completely agree with you that network is a huge problem. I have seen many situations like people rely on, for example, on communication between services or services and Kafka and so on. So when they do some operation, after that push message to Kafka, and I assume that operation is always successful, but of course it can fail, and you have explained many different reasons why. But still, I thought you would just answer data.
Yeah, I think you're right. Sorry, I didn't mean to interrupt, but I understand what you're coming from. But looking at things from first principles, bottom up, I think all problems with data, arise around the fact that you have unreliable networks and that you have latency and so on. And so I think the way it's usually surfaced is that it makes it very, very hard to work with data in a distributed system, and having data consistent and having sort of a valid, or I wouldn't say a single coherent view, because often that's not impossible, but one that has enough guarantees to make it useful, if that makes sense, across a distributed system. So
Yeah.
I don't disagree. The data is usually the hardest thing, but the reason why data is hard is because of the network. So.
One of the reasons is the network, and completely agree, because they are connected. But also the second phase of the same problem. Like, for example, what kind of storage are you going to use? Like, for example, store data as events, or maybe stores the snaps of data, like using the old SQL database. The second problem is, for example, if you want to implement stateful service versus stateless versus stateful service. So,
Right.
so data have many different phases, and one of them is network, but there's many different perspectives how we can implement the same. Also, why we decide to implement a distributed system, because you want to handle probably much bigger load than in the past. So you have to be able to store, read data, process, and so on. So
Yeah, no, absolutely. It's this was one of the luxuries that we had when we had a classic sort of 3-tier architecture with a single database and no distributed system. That data was always consistent, it was always available, it was always accessible with quite low latency, and it made the world simple, and that's why we saw a lot of patterns around stateless architectures because if data is always available, it's reasonably reliable, and you can access it with really low latency, even though it's over there somewhere, then you can simplify the application layer a lot. But in the world of distributed systems, exactly as you said, we have to embrace a stateful architecture. And this is something sort of that I've been with me, the last decade or so, that a lot of the systems that fail at really, really large scale or really, really high availability are the ones that still embraces a stateless architecture. Because if you always put the state somewhere else, it's usually incurs a quite big network overhead to go over there, so it increases the latency. And if you instead of having hundreds or thousands of users like many of these monoliths, if you put them on the internet, you can easily have hundreds of thousands to millions of concurrent users. Then you will simply choke on that. And then you also have the availability problem. If that thing goes down, the thing, I mean, database or data storage, then essentially you're screwed. But if you're instead having a way to having data in memory but still durable, then you can always serve your customers. And if you rely on database sharding and try to partition your data, then you don't put all the eggs in the same basket, so to speak. I mean, if one database goes down, you can have failover mechanisms to redirect to another one, and that can sort of take over. So there's a lot of value of having data being partitioned and replicated across multiple different things, because the definition of not being available is really to only have one thing, because if the one thing goes down, then you're 100% unavailable. So it's risky.
So we mentioned about partition tolerance, about availability, but also this consistency, which is also very important. So now developers have to balance between those three components and choose whatever is the best for them. And yes, I think people still try to use the old approach and prefer consistency over everything else, but it's not always the option. What recommendation do you have to implement or design the proper distributed system? It is even possible to have one design which we can apply to any kind of problem. Of course, any kind of distributed system.
That's never the case. That's why I didn't mean to interrupt, but I just want to emphasize that's never the case. And that's why we need to work with from first principles and have like composable patterns and sort of architectures, but composable patterns and ways of putting the system together. So
at least, can you see some technologies, whatever, what can help to implement different distributed systems, or maybe better? What can you see something what should then be used to implement distributed system, because it almost always fail?
We need to when entering distributed systems, we really need to understand the constraints as well as the opportunities. Everyone's excited about new thing, but it's also the constraints and the sort of and the problem space. For in this in the world today, it's usually around cloud, but also around edge. And I it's one very important thing for me is always to really design for failure. That's one thing that you have to expect that failure can happen at any time. Really, in a it's really true for monoliths as well. Can be due to bugs or whatever, but it's exponentially larger in a distributed system. I think it's because it's really inherent in the problem space. So you really have to assume that anything can really fail at any time. And I think the best way is to change the way you view failure. In Java we call them exceptions. But there's really nothing exceptional about failure. It's just and something that happens that sort of triggers some sort of event. If you have loose coupling with sort of stateful autonomous components, if a component fails, it can actually fail in isolation. If you have if you have decoupling in both time and space, and we can talk about how we can build such systems. But if each component is truly compartmentalized, contained, then each failure can really just be an event in a way, sort of a notification, telling other components that this component has failed. And then they can react to that. So if you build a system that is event based, for example, then failure is just a natural event in the system. So it's really the way I view failure is really that it's just a natural state in the application lifecycle or in the component lifecycle. You have the component starting, stopping, idling, pausing, and failing, and there's nothing exceptional about it. There's nothing to be scared about. It's really something that you just design for and fully embrace, and it usually makes your life easier. So that is one thing. Another thing that also has been, in my experience, is really important is the concept of location transparency. Yeah, and what that means for me is really that you have sort of one single abstraction, sort of programming abstraction, communication abstraction across all dimensions of scale. And what I mean by that is that that if you have a component, the way you design your system shouldn't dictate where things run. Essentially, the topology of the application. If you have an enough high abstraction in exposing the right constraints and primitives to work with the network, then it really doesn't have to be any difference if you're communicating between two components A and B across different cores, CPU cores, or across different nodes, or across different data centers or different clouds. If you have a programming abstraction that is truly location transparent, then the topology of the application is not fixed, meaning that it's not a design concern, it's not even a deployment concern. because it liberates the components to move around in the cloud all the way out to the edge or whatever without anything breaking. So the design allows for fluidity and flexibility, which I think is extremely important. And of course, this requires you to have asynchronous communication. Because asynchronous communication really gives you, sort of breaks free of this strong coupling between components. So it really gives you a way to become fully decoupling time, because the temporal aspects is sort of broken up and in space. And it's this decoupling in space that allows for location transparency, and that allows for isolating failures that I just talked about. And so
It's very interesting because you see problem from different perspective than I. Like, for example, you see a problem from principal perspective, like, for example, that location transparency and so on. And you have created a very awesome library framework to solve such kind of problem, means Akka. But when someone will ask me about what kind of problems I see, the most common problems I have seen ever, like 19% of project has the same problem when you have database and Kafka in one project. So when you have received request, you have to store something in database, and after that send message or events to another system. It is almost always broken, like, because people assume that Kafka is always live. They can commit transaction or store data in document database, whatever, and after that send message to Kafka, and sometimes it fails. But what you have mentioned is just a reason of that failure. So maybe what we should avoid to not make such kind of failures, in your opinion, or what kind of technology we should avoid? Maybe there's nothing like that. So I'm just curious if you have an experience.
I'm hesitating because everything has a purpose. Sometimes so it's very use case dependent. There are. As I said in the beginning, just mindlessly bringing in tools that used to work in the non-distributed world sets you up for failure. That said, there are tools that work well in the monolithic world that can absolutely work well in a distributed setting. But there might be adaptations you have to do, and you have to perhaps shield them from the rest of the system and so on. For example, having sort of always assuming strong consistency across component boundary or sort of product boundaries might be quite challenging. In the monolithic world, it could be quite easy. But in the distributed world, that's just assuming that that everything can be transactional all across, across all, what pubs are brokers, all the way down to the database or so on. It's very, very hard. You have XA, you have two-phase commit and all of these things, but as soon as you introduce locking, you introduce wait time. As soon as you introduce locking, you're running the risk of exhausting IO. And also, one a very important thing is as soon as you have transactions and have locking, you essentially put, making sort of designing a system where each sort of product or component, sits in the other's lap in a way. I mean, you have them strongly chained. So you can easily end up with if the thing fails, it can take down the next, that takes down the next, that takes down the next. And then I remember when I wrote EJBs in the back in the day, and you sort of just turned on sort of clustering in WebLogic and so on. It was not that uncommon to end up with cascading failures, having one failure to taking down eventually the whole system, or if it doesn't take them down, just cripple it enough so it can't be useful. So I think this is something that you really need to rethink. I think transactions has their place for sure. In strong consistency has their place. We can talk more about that, but I think you need to be careful about it and apply it selectively, just in the right places. That is one example. I'm sure there are others as well.
So you was one of the author of Reactive Manifesto. It was over 10 years ago. Is it still valid in your opinion today?
Yeah, no, it was written sort of back in the day. You have to understand, a lot of people were new to cloud and new to distributed systems, new to multi-core even, and how to manage. It's hard to believe nowadays because there's a multi-core everywhere, even in your phones. But a decade ago, people were still struggling with how to build systems for multi-core, multi-node, and multi-cloud, of course, and they didn't even exist, really. At least it wasn't on people's radars. But anyway, it was a lot of confusion. It was a lot of different sort of communities and people, doing different things, using different terminology, different vocabulary. It was sort of written as sort of first like a call to arms, like inspire people to dare looking into this new world, and also having a structured way of thinking about it, even though it's very simplistic, just try to boil it down to some basic principles or traits that you would like to overcome or embody in your application. And it was also trying to set sort of a terminology, like or the set of vocabulary. That's why the Reactive Manifesto has a glossary as well. That goes also quite deep into the different definitions, because I learned that when talking to other people in other communities that we all had the different ways of talking about things. So it was an attempt to try to unify, good thinking across many different, domains, industries, and community into a single sort of framework to think in a way. You asked about its relevance. I think that when we wrote it back in the day, it was fairly new ideas. I'm saying that almost in quotes, because it's really not new ideas. It's really ideas that have been around since the 70s even. People have built systems in this way, and so in the right way to tackle these challenges for a very long time. But for most people, it was quite new, and I think that it's becoming honestly more and more relevant, every year, because more and more people have been forced, driven by business needs to deploy distributed systems and to run in the cloud and to start tinkering with the edge and so on, and now you have the whole agentic wave, that even will make these the need for truly distributed components and meaning dealing with massive amounts of scale even more important. So I think every year there's a new wave that sort of points people to the principles of the Reactive Manifesto and the reactive principles in general, that sort of backs up the Reactive Manifesto, I think.
Yes, I completely agree. Still valid, and even it's become even more valid probably in the past. You have mentioned that you're also Akka author creator, and how we can use Akka to implement distributed system. It is good technology for distributed system. I know the answer, but I'm very curious.
I'm biased, but my answer is also backed up by hundreds of thousands, actually, or millions of users, and many and thousands of customers, so being happy with it. But I really think that so when I created Akka in 2009, it was really to try to address all the headaches around building distributed systems. So not all, but try to mitigate some of them at least, and having a structured way to do so. And it's Akka's based on the actor model, and the actor model has been used since the 70s to really address some of these hard challenges with distributed systems, with building in truly parallel systems and systems that can scale and that can live up to immense levels of resilience because it has really failure models built in and resilience built into the model. But actors are really interesting because they do abstract over the network, like I talked about, and that's why I've been so excited about actors from the get-go. It's really great for distribution. But the interesting thing is that by being great for distribution or building distributed systems, thanks to location transparency that I talked about, it turns out that it's also works equally well, I have to say, for solving the multi-core challenge as well, because the abstraction of actors sort of scale in a way. I mean, in terms of abstraction, it scales from small to large, and it's I think that's one of the really compelling things about actors, and one of the reasons why it's been very popular. These actors is if I should first try to explain what Akka does, and then we or is rather, and then we can talk about more what it does. So actors are these stateful, fully autonomous, and really small components that does one thing and one thing only. So it really lives up to this classic microservice principle that each service should only have one reason to exist. The way they implement it in Akka, at least, of course, it can be abused, and you can have a very inefficient implementation. But in Akka and Erlang, for example, and other popular active frameworks, they're extremely lightweight. So with Akka, I can easily run millions of actors on a single laptop. They're only sort of capped by RAM. And these actors then multiplex on a thread pool to run, sort of being scheduled as needed, or onto an actual thread being scheduled on an actual core. So it's really, it gives you a very different sort of tool to model, not just build hack together, but also model and think about how you build distributed systems. Because if you have all these really small, super lightweight components, then they can easily create lots of them, and you can almost end up with systems that have almost like a sort of inspires from nature, in how ant colonies work, or bacteria or whatever. So, and where failure in one of the components can be managed by the others, helping out or stepping in, so to speak. So you end up with a system that can almost self-heal, and that is extremely resilient to failure. In actors, community are always communicating through asynchronous message passing, meaning asynchronous messaging, and this gives you this sort of division between the components, allowing them to be completely isolated. And in Akka, each failure is reified as a message that can be sent to what is called its supervisor. So you can create these supervisor hierarchies where each actor, as a parent actor, can sort of spawn multiple actors and be sort of supervising them in terms of failure. And if one of the child actors are failing, then the supervisor will get a notification, and it can then, in a safe context outside the failed context over there, it can be on another thread, it can be on another node in another data center even, but it will still get this notification and can act upon it. And choosing to restart the actor on the same machine, if it failed because the machine went down, it can choose to respawn it on another machine, and it can just continue to do its work. So it's really embodies asynchronous message passing. It embodies failure management built in. And it also embodies full location transparency, because these actors can just move around, and since the sender and receiver are completely decoupled, and the sender never even know where the actor he's talking to is running, that actor has the freedom to actually die and be reborn without the sender ever knowing that happened. There might be some incurred latency, so assume that some fishy things going on, but from the context from the perspective of the sender, nothing has really failed. And the same thing, this actor can be relocated to another node, or replicated or so on, and it's nothing that affects the sender of the message to that actor. So you have this fluidity that where actors can come and go, and they can move around in the cluster sort of seamlessly, which is a very unique sort of property of actors, and makes them very suitable for distributed systems.
In the past, I don't know, maybe 10 years ago, I had a very interesting project about with payments, because you have mentioned about that nature, you just simulate nature. And I completely agree with that, because in the past, as I have mentioned, I had a project with payments. Before Akka, it was implemented twice with a lot of synchronization logs inside. It was terrible. So there was almost one bug after another, so we wasn't able to fix that because there were so many different conditions, so many inputs. And when we have re-implement to Akka, and it was 10 years ago, so it was one of the first projects we have done with Akka, everything becomes so simple. Any synchronization, there was few actors, each of them was quite simple with only one reason, with one activity, and it was like a magic. Project was super easy, and it was perfectly without any issue. So I know what you want to say, but also I want to touch location transparency, because before we have discussed about Akka, you have mentioned about many different problems related with distributed system. One of them was location transparency, accept failure, and so on. And what is interesting, when I use Akka, I never have to thought about that because it is implemented there. It was awesome, and you just use those components. Sometimes I use different technologies or help project which use different technologies, and I see how people have to fight with that. Like, for example, implement that they have to handle failures and so on. But Akka is even more. It's not only actors, but we have also persistence, cluster, sharding. So you can use a couple of components to build a really distributed system when you can deploy to any cluster, which can handle partitioning issue, which can distribute the data between nodes, when you can scale up, scale down very easily. So for me, Akka is one of the best technology to implement distributed systems. And Jonas, last time Akka company released Akka Platform. How you can compare to the former Akka? Because in the past we had libraries, set of libraries when you have to connect together to implement your service, but now we have Akka Platform. It's something quite new. I know a lot of people don't know what it is. So can you explain what is Akka Platform, and is it worth to use it?
Yeah, thanks for the nice words about Akka as well, and I'm happy that you have good experiences with it. It makes me really happy. One thing that I have to say, as sort of a critique to Akka, is that I want to say that first because it sort of leads into why we've implemented the platform. And that is that it's so honest about the constraints, and it gives you like a complete open-ended toolbox. So it can sometimes be overwhelming for users to know what tools in the Akka toolkit to use. I only touched on the more sort of principles, behaviors of actor systems. But as you said yourself, actors, Akka has a ton of different modules. That does so many different things. We have modules for streaming, for pub sub, for clustering, for data persistence, for event sourcing, for doing like streaming read projections. We have edge, client that you can run all the way out to the edge. And it has like a full integration patterns library called Alpaca, where we implement most interesting protocols and like drivers for different products, Kafka and Pulsar and all kinds of stuff. And it can sometimes be overwhelming to know which components to use. For a distributed systems expert or someone like, as seasoned and skilled as you, it's quite easy, I suppose, to navigate it because you know what you want and you've been burned so many times that you know what doesn't work well, what works. But it can sometimes be overwhelming for new users, So it's an educational challenge. Once you get your application built, it usually works flawlessly and it's really, really as simple as it can be, I have to say, while making the most out of the cloud, because that's really been the design philosophy for what we know called Akka libraries, the sort of classic actor model Akka. It should be as complex as necessary to allow you to build the most effective and reliable thing in the cloud or at the edge. Akka Platform is really a way to try to make things easier. And another thing that I didn't, that we haven't talked about is sort of this whole, ecosystem around, that's been coming up in terms of infrastructure. That in Kubernetes is really amazing, I think, and there's really it's really revolutionized how we can build systems, easier. But it's sort of a blessing with the curse, I think, because Kubernetes comes with first, of course, it comes with its own problems. If we ignore those now, it comes with the whole ecosystem, the whole CSC and CF ecosystem of tools, and it's been, growing sort of completely out of proportion, almost in a way. That is my critique. That is often sometimes very, very hard for developers to manage that complexity. To understand what tools to use, even which ones you should pick, then understand how they use, then understand how they should be composed together into a single system. It's so the richness of the ecosystem can really make the developers simply drown in complexity, I think, and also just how to manage all of these things once you actually put it together. It can really be hard. So one of the things that have been driving what we have been doing at Akka lately is, try to really sort of, climb this ladder of abstractions and provide useful abstractions that try to abstract as much as possible. Because most developers, I don't think they actually need every single knob. They might think they do. And if you're like an SRE that loves what you do, sure, but if you're a developer and running DevOps and stuff like that, it can be overwhelming for developers to have everything available to them. What I've been thinking about is that what can we do, to make lives easier for developers? And when you really distill down the essence of what developers need to do, it's, you might argue about this, but this is the way I view it, is that you want to define an API for your service. How does the service communicate with the outside world? You want to define your data model. That's inherent to the business and how you model the world, the business problem. And thirdly, you want to implement the business logic. But apart from these three things, ideally, what if everything could be sort of just abstracted away? All this infrastructure, all the decisions, all the way of thinking into operationalize. What if all of that could be just abstracted away? And you as a developer only have to focus on these three: API, domain model, meaning data modeling, and the business logic. So this is really what we've been trying to do with Akka Platform, having a way to like abstract over everything but that. So user-facing, the Akka Platform has a very guardrail, very opinionated SDK, software development kit, which is quite unusual for Akka, but that has a history, as I said before, being completely open-ended, like a toolbox. It comes with a prepackaged SDK with 6 different sort of composable components. You have entities, that where you model your state, that's sort of similar to the entity in domain-driven design, if you know that. You have an endpoint abstraction that allows you to expose your API, just using annotations, simple sort of JAX-RS style. You have a view, so you can have like streaming queries down to the data storage and having those streamed all the way out if you want. You have controllers, you have timers, and you also have workflows. Because if you build these services, often you need a way to compose them together into like more long-running workflows, business processes, and so on. All of this is like almost like a thin layer on top of Akka. we talked about earlier, the actor model. That's, the underlying is what we now call Akka libraries, and this high level sort of DSL in a way, domain specific language almost for distributed computing, but in the form of an SDK like sits on top. And it really tries to minimize choice, making it easier to move fast because there's less things you have to worry about and less things you have to do. So that is the developer facing thing, together with that, we've also built now sort of a really hyper productive, like local development environment where you have a way to have really fast turnaround time. We have a local console with, they can debug your events, and you can put everything is automatically gets deployed into a sandbox that you can run. And this local development environment really mimics production. So if it runs well, satisfying all tests on your local machine, the only thing you really have to do is like press deploy, and then it's like thrown up into our cloud, onto our platform, the Akka platform, and we just run it for you. So it's and there you have all, of course you have operational capabilities, but we only expose the knobs necessary for you to understand what's going on and fix what the basics, the important things. We have of course transparency, observability, and all of these things, but we run it really for you. We have an on staff 24/7 SRE team that really runs your application for you. It's never been easier. It's a little bit like AWS Lambda. You just write a function and throw it up to AWS, but we have a much richer component model that sort of try to embody all the principles and things we talked about here. And I can also just say that we have the options in terms of deployment for either just running serverless, sort of pay as you go. It's very, very easy. You just build something and throw it up there, a POC. The interesting, the POC is very often your production app as well, because it's really not much, in our experience when we work with clients, usually as works out of the get-go. So, but it's perfect for like startups and smaller projects perhaps, but larger enterprises usually want to go with our BYOC and bring your own cloud model where we where companies actually run the app in their own cloud. But we deploy into our control plane that does all the heavy lifting, and we sort of manage that for you. But the data resides on the customer premise, which is very important for them, for compliance reasons or security as well. Interesting though is that we just last week actually released a sort of new variation of that, in which we sort of package the SDK in a way that you can just put it into any Docker container and just run it yourself, without us having anything to do with it. So if you really want to like set up Kubernetes and run it on whatever Fly.io or whatever it is, but still want to get the benefit of the SDK and the fast development environment and all of those things, you can just run it as you run any Docker app. That is quite new.
So Jonas, you've mentioned that it was designed to help developers. It's true, because it's very easy to implement whatever you need. But also it just help business a lot, because business don't have to pay a lot for development, for DevOps stuff. They can just implement very quickly, deploy. And time to market is just very short comparing to whatever else. But also for me, Akka Platform is just the next evaluation of the development. So when I have to use something else than Akka, and I see how people solve problems which are just solved out of the box in Akka, I wonder why you have to do that. So it's like, it is there, just use that technology. But last time when I have played with Akka Platform, I have discovered how easy it is to deploy application and create new application. And now, for example, when I have projects when developers still use Akka and they have to set up, for example, clustering, deployment, even infrastructure to deploy, I wonder why we have to do that. It is there already. But also from development perspective, we have to implement some kinds of workflows using Akka. It's quite easy, but you have to implement. You have to connect, for example, Akka persistence, Akka projection, and then eventually you can just implement that workflow. But now it is there already. So it's like the next step. So each time when it's new version, it just simplify life. So you don't have to implement those not trivial. They are quite complicated, even very complicated components, but they don't bring any value to your business, and you can focus on that, on your core, like instead of context and everything what is technical, just provide business value. So for me, at least, is the biggest change. So you pay, of course, for that, but you save a lot of money on development, on infrastructure, creation infrastructure, and so on. So eventually, it's much more cheaper than develop yourself.
I agree, and you're absolutely right. I started with the developer that we really wanted to simplify things for developers, and I think we do. But you're absolutely right that what Akka brings, or Akka Platform brings, that we haven't really had in Akka before, is an opinionated way that makes it easy to run things. It's the operational side of things.
Yes.
Just one example, for example, is Akka Platform or the SDK. If you build components in the SDK, the runtime supporting it really allows you to run things across multiple regions or even multi-cloud. And the interesting thing is that all of these things are fully enabled for you out of the box. So the only thing you need to do as an operator coming in, you can just log into the console and change the topology. You can say, now I actually want my application to not just stretch these AWS regions, but I also want to stretch it over to Azure or Google Cloud or whatever. And it's just a simple button click, bam, and the whole cluster reconfigures and it rebalances across all of these, or this new environment, being multi-cloud or multi-region or whatever. So this is one example how we've, been working years with the hard stuff, and we've been able to abstract it in a way so it's just a button click, more or less, which I think is quite mind-boggling looking back what you had to do like a decade ago. So that is fun.
Yeah, so you have two options: just implement everything yourself, means also infrastructure, versus this something what is already there, implement that core of your business and deploy it with one click. So, okay, Jonas, we have discussed about past, like Reactive Manifesto will still is valid, and in my opinion, it's even become valid than in the past. We have discussed about Akka, so about current times, but how you see future of distributed system?
Yeah, there's two things that I'm really interested in, and that we've been, I've been researching, and that we've been developing, around the last few years in Akka, and that is, the first thing is edge. They're really in order, but the first thing is that comes to mind is edge computing, and making it really, really easy for people to build joint cloud to edge systems. But I just want to say the second big thing is agentic AI, Gen AI, and it's being really, everyone's raving about that. You can hardly read anything but that if you go onto social media nowadays, and it's really a frenzy, and it's, you can argue that it might be inflated, all the promises and hype and everything, but I really think it's true. It's really, and most of the things are true anyway, and it's really here to stay. So, and it's an interesting thing is that it's almost a perfect fit for what we talked about here. It's actually, agentic AI really requires you to build systems in this new way. As I said, it's really on the rise. Everyone's talking about it, and everyone's super hyped about it, but also everyone's very, very confused about it. What does it really mean? But I think it's here to stay. I think it really is already, but will even more so revolutionize our business, or industry, and the world at large. I think, and it really opens up for use cases and being able to do things that you couldn't do before, and I think that's really the exciting part. You shouldn't just jump onto AI because everyone else is doing it, or FOMO, the fear of left behind. There's a little bit of that as well. Large corps are just mandating AI, but they perhaps don't really have a strong story for exactly it. But I think it's all coming together slowly. This is always the case when something new exciting comes. So it's nothing to be surprised about. Interesting thing is that the way the industry has defined, the Gartner and others, are defining agentic, is that it's stateful, autonomous, components working together, components called agents then, but it's really components that we talked about. So stateful autonomous components that work together. to solve problems, using, many classic patterns we've seen, workflows, pipelining, routing, and so on. Sometimes we're working, as a graph and so on. We see all these patterns coming up, but it's really nothing new. It's really, honestly, what Akka's been doing for 15 years in a way. We've really been, I don't want to, boast or anything, but I feel like we've been helping clients build sort of agentic style application for quite some time, and it's really what the Reactive Manifesto was all about as well. So that's why I said, a few minutes back, that talked about Reactive Manifesto, that's becoming more and more relevant, because it's clear that this sort of this agentic AI wave, really requires all these principles. Truly, it's not that you can, get away with, being a little bit sketchy here, a little bit there, and use a little bit of statelessness here, and so on. I think it will radically change how we force people to change how they build systems, and the reason why is that it has a very different performance and cost profile. The performance profile really differs from CRUD. The classic, create, read, update, delete pattern using a regular SQL database. If I remember correctly, databases usually have, in my experience, between 10 and 30 milliseconds perhaps for each call. And LLMs latencies, large language models latencies, even if you run your own, but also even more if you call an external one like OpenAI and Claude and so on, they're usually like 100x. So like really two orders of magnitude. So the latencies are a lot higher, and the cost is like immensely larger. Some articles that I've been reading, like, says there's anything between like 10,000 times to almost 1 million times for the more sophisticated models, more expensive than running just a regular database call. So it really changes the way you think and how to design for. Another thing that, we can't prove all this yet, but I really, we're talking to a lot of experts in the field and so on, there's really consensus that this whole agentic AI wave really requires a very different magnitude of scale than what we've seen, with first cloud, but also even mobile. With that was really another leap, from cloud, because in the mobile era, many applications, they were perhaps in the 10K transactions per second, roughly. Anything between 2,000 and 10,000, was not unusual. But in the agentic AI era, if you envision a world where each user has multiple agents working for them, so instead of having one user doing all the requests, you have multiple, like 10 or 20 different agents representing the user, doing calls constantly and working together, sometimes continuously if you have, if you have that type of use case. I think you will end up with like 2 orders of magnitude more, sort of LLM calls, meaning transactions per second. So for going from 10K perhaps to 1 million, and how do you deal with that? You can't use a classic just 3-tier stateless architecture for that. That's why this whole agentic way requires you to have lightweight stateful autonomous components. Autonomous meaning that they can actually act and decide on their own, on behalf of the user, which is also a requirement, and also something that I think Akka can really help with. Another problem that we're seeing, it's more present, and that is a lot. As I said, there's a lot of hype, a lot of excitement, but many companies are failing to go from POC to actual production software. I remember I read a Gartner survey a few weeks back that said that like more than 50% of all AI or agentic projects fail to go to production simply because because it's many of the tools, early tools make it easy to do type of POC type of systems, and they focus on simple, very simple agents just doing like single calls to the LLM. Of course, deploying that to production, is fairly easy and run. But the problem is like operationalizing it across. I mean, if you want to roll it out to hundreds of thousands of customers, that many of the early tools, startups or whatever that you are using in to implement your agents, haven't really gotten to a solid platform for actually running that at scale. And doing that yourself without a platform is even harder. And I think this is something where Akka can really help. We've been running. They weren't called agentic, but like machine learning and even sort of what was called Gen AI, type of workloads for our customers for many years, and it's really proven to work, very very well. And we provide, as I talked, but the whole point of Akka is that Akka Platform is that it's a holistic platform that will take you from development into production and have you excel in production. With the right knobs, being able to scale out and as needed, and so on. So, some of the things that I think are really important that Akka embodies that are important in the agentic world is as I said before, that failure is a first-class concern, and that's becomes even more important in agentic, I think, than in distributed systems, because in agentic you have all the distributed systems problems, but you also have all the problems with LLMs that you can't actually often always trust the LLMs. They can hallucinate, they can give you all kinds of weird things, or weird answers, and of course you have the latency that adds to the cost, making things more brittle and so on, and often you need to verify the actual result from the LLM, perhaps with 3 other LLM calls, to see and do some sort of consensus call, or you need a human in the middle to actually verify that everything came back. So there's a lot of more failure concerns that you have to deal with. So they're sort of compounding, with LLMs, I think. So, and this is something that Akka's really doing really, really well, since we, agents that can move it's built in that they can restart, isolate, and they can just recover autonomously if something goes wrong, as we talked.
It's one difficult question. So you're right. In agentic AI, we might have much more requests than in the traditional systems, and of course, it requires more computation power. So it is possible to reduce cost for agentic AI or future distributed system, or it must be just very expensive and there's no solution for that.
Yeah, it's 2 different things. I think that you can be very, very efficient when it comes to the system using these, and that matters, because if you have millions of transactions per second, and each transaction is very, very pricey, you don't want to do any more calls than absolutely necessary, and you don't want to incur if the latency is already quite high, even though network latency perhaps doesn't have that much, if you have millions of requests, hours and hours and hours, I mean, it all compounds. Small things matter, I think, and in the long run. So having a way to having the platform and the application being as efficient with data, with decision making, having it as low latency and as possible, and also having it as resilient as possible, meaning that you shouldn't use blocking IO down to LLMs and so on, and most libraries still use that. So we have a long way to go there in general, but I think that is something that's in our control, and that's why we should focus on that. The actual running of the LLM is less so, at least for us. We don't build LLMs. We use the models that are out there and so on, and they are, I'm sure prices will go down eventually, but the prices are high because they are usually quite resource intensive, but this is sort of, as I say, it's outside my control, and I think a lot of developers' control. The LLMs are what they are. Even if you run your own, it will be very, very expensive to run. So, and we just hope the research, gets further and further towards more simplified model, like DeepSeek, and for example, was one. I don't know if you read the paper, but they were able to cut it down, if I remember, to like 1/10 of many other models.
There was
so,
yes.
Yeah, so it's a lot of interesting things happening there, but I think we as developers, need to focus on what we can do really well, and or just delegate to a platform like Akka that have a decade or more behind us trying to make things as efficient as absolutely possible. So
How quickly I can create agentic AI using Akka Platform?
yeah, as I said, if you use the SDK with these 6 high-level components, I think we have shown customers over and over again, and they've seen it themselves. That they are actually all you need to implement these type of systems because we haven't talked about it, but one of the things that Akka really embodies, and I think is very, very important, is a fully event-driven architecture that is based on event sourcing. Akka sort of really embodies event sourcing and everything being fully event-based, and that I think is key to building efficient agentic systems as well, and really stateful agentic systems. For simple systems, you might have one agent, but most people are raving now and talking about, the possibilities of multi-agent systems. And if you want to build multi-agent systems, it's actually quite easy in Akka. You simply write a service within, that's an entity plus an endpoint, and so you have the API and you have your data management, managing the domain model and mapping it to storage, and then you have the workflow component. And the workflow is really the way that you can stitch together these agents into ways of collaborating across multiple different stages, and you can go back to stages. And if things fail, you can just resume wherever you were, and so on. And each of these stages, I envision is an agent and with an LLM call. So you might come into the first stage, you do an LLM call, you get some sort of response back. You might want to go out and do some call some tools for getting more data. But before you do that, because these are also expensive calls, you might want to verify the response. So the next stage might actually have a verification stage where you call in more LLMs, to verify the data, unless you want a human coming in and looking at it, which we also can do in the workflow, and so on. So it's really important to have a very structured and high level way of stitching these things together. And the workflow is really like an FSM, a finite state machine that allows you to do this in a very structured way. So in my experience, our customers' experience, it's very, very easy to do. We've been doing POCs, within 48 hours for several of our clients coming in with log. And one of our clients came in and they had really been trying to build something, sort of implement their agentic use case with other tools. I don't want to name any names here, but they were really, really struggling, and they had been going on for 2 months roughly, and without any serious results. And they came to us, and we, in our engineering team, or rather professional services team, implemented essentially the whole POC in less than 48 hours for them, and that lived up to their latency guarantees. So I think that speaks for itself. That it makes it very, very easy to dive in, and I think one of the key things that it reduces decisions. There's one way of doing things, and one way to putting components together. You have to choose the right model, of course, and so on. But from the agentic part of things, I don't think it can be much simpler. And you don't need to worry, because you can just throw it up in our cloud and we run it for you, which is the second really, really hard problem that customers are facing. So.
Now, let's assume my company has implemented SaaS application using completely different technology than Akka. We store data in one of the databases, actually in many databases. Mm-hmm. And now I want to implement Agentic AI to work with my SaaS application. It is possible to implement it using Akka Platform, or maybe I have to migrate my SaaS application first to Akka Platform and then implement Agentic AI.
Two things here. First, you can definitely run Akka side by side of your existing Agentic AI solution. Nothing prevents you from doing that. We have a lot of good integration points and ways of working with an existing system. So by sort of extending it. But I do think that also if you're lucky enough to not lucky enough to have sort of a clean slate, Akka can provide a lot of value here as well, because it allows you to implement your enterprise side of the system and your agentic side of the system using the same SDK and with the same components for two completely different purposes, but and all running in the same environment essentially. So there's really no difference between your SaaS and enterprise app versus your agentic app, and I mean difference in how you run. No, and no difference in how you in the cognitive sort of baggage, or because it all looks the same essentially. I mean, agents are services are agents. It's just how you use them that is different. So that's my thoughts on that.
Okay, Jonas, as you have mentioned about edge computation, how important it is and how we can just implement?
I mean, first I want to say that I don't like the word edge compute or computation, simply because it puts an emphasis on compute, and I think that's the way people looked at edge in the past. And I'll explain what I mean by that.
Which word I should use?
Edge systems, because I really, I think the big problem with just talking about edge compute, is that it misses out on the data. I think the data is probably the most important thing why you want to move to edge computing, or edge systems. My definition of it is that, I think the reason for implementing edge at all, is really to be able to serve your customers where they are, right where they are physically, co-locating your system with your user, because if you're able to co-locate your service with your user, you have immense low levels of latency because you're right there where the user is. So you can just serve him or her directly without any real latency at all. And the other one is availability, and that is something that most people don't talk about, but I think it's probably even more important. And because if you have, let's say that you have a definition now beyond compute, so you actually have compute, data, and end user, in the same physical location, all co-located, then you can serve your customer or your user regardless what happens. The connection to the backend cloud might go down. The connection to your peers might go down. It doesn't matter. If you have the data and the processing right where the user is, you can always serve the user, even though everything crashes and burns around you. So that's a very powerful concept, and a lot of people talk about local first software when it comes to this. And local first software really sort of try to invert the relationship or the dependency between your edge service and the cloud. So instead of the cloud being the master that always serves the edge service, the edge service is really fully autonomous and doesn't depend on the cloud. If the connection to the backend cloud is there, it's a luxury. It's definitely useful. Let's use it for backup, for more thorough processing, perhaps running, Spark jobs on data analysis or whatever the cloud is really good at doing. But but it's only sort of a luxury, something that you can use when it's there. You're not dependent on it. And if you build your systems with that mindset, then you can be extremely resilient, if that makes sense. So, but the key here, is really co-locating physically co-locating user state and processing. And another very important reason for this is all these mandates that are coming around for compliance, regulatory concerns. Where you have to ensure that your data never leaks to specific physical location. And I think edge can really, really help with that, and having a very, very fine-grained way of managing that. And I think also, why I'm really excited about it is that for me it's not just about edge and cloud, and these are two completely separate things. But it's really that one needs the other equally much, I think. So the way I think about is that what you want to do is you want to take your cloud system, you want to extend it out to the edge as far as possible, but you still want to have it being one system. You don't want to have building your edge system using different tools, different design patterns, different things, and then you have to stitch it together with the cloud system. Ideally, you want to have it as one single system. And so it removes or sort of rather blurs perhaps today the boundaries between these things. So I usually like to call them like cloud to edge systems. That the cloud to edge is like a continuum. It just continues all the way out to the edge. And Akka naturally is really perfectly suited for that with its location transparency. You like really lightweight stateful components that can really run anywhere. They can run great in the cloud. They can run great at the edge. But we've been working very hard, the last 4 years of the final pieces to making this sort of true. A lot of our clients, for example, run Kafka. But Kafka doesn't really run well at the edge, if it can run at all. So we've implemented in our own brokerless PubSub module that allows you to do like PubSub over gRPC without a broker. It's extremely efficient, and for what it does, it even has lower latency and higher throughput than Kafka. And we also had to replace storage. You can't run Oracle at the edge, but we implemented a very lightweight local storage for each one of these edge components. And we sort of package that up as an edge client that you can just put out at the edge. It simply extends all the same thinking. Is actor modelish based, It has built-in event sourcing, really great local, fast local storage. It all talks about PubSub over gRPC and so on. So it effectively allows you to stretch out your application all the way out to the edge without anything really changing in terms of how you think, which tools to use, and the architecture-wise and so on. And since these components are location transparent, they can actually move, which is another really important requirement. Let's say you have like mobile user, perhaps even cars, that are actually constantly on the move. And if you want to be able to meet them as close to where they are as possible, if you have a moving car, you actually might have to migrate the actual component between, data centers close to the cell towers that they are, as they drive through the country, which of course requires a model that allows for mobility and location transparency and so on. I really think that this whole agentic wave will also sort of, I wouldn't say merge, but start taking advantage of all these edge capabilities, because there's a lot of data was shuffled around when talking to these LLMs, and if you can serve your users local, as close to them as absolutely possible, there's less data shipping, and you can also increase, as I talked about earlier, the availability, guarantees for serving these agentic, workloads.
Do you have something specific what means edge? Because it might be different device, different component when you deploy applications. So do you have something specific, for example, it's like end device or servers, towers, whatever, close to the user?
Yeah, it's a little bit blurry. Edge means different things to different people, but the way our clients usually are deploying things, so that you have the central cloud, you have regions, where you deploy things, but it's still sort of cloud. But then you might have local sort of smaller sort of mini clouds, that sort of strategically positioned out at the edge, serving serving users, often close to cell towers and sometimes even inside the cell tower itself. But then you have and I consider that edge as well.
Mm-hmm.
But the final step is actually running on the devices themselves. And that could be running inside the actual cars, running inside the actual mobile phones, or running in the drones or whatever. So, and the Akka Edge client that I talked about actually can run inside your drone. It's a Rust-based implementation that runs natively on ARM hardware. So it can run really efficiently, and it doesn't require much resources at all. So in the Akka case, I would probably run a regular Akka application all the way out to the cloud, to the edge data centers, while I'm using this Rust-based edge client to run in the actual device, and stretching it out to the final hop, so to speak.
And what about data? So most of the data you have at edge, but sometimes some of the data you want to send to the cloud. How it's solved? What kind of data? You replicate all of them, or maybe you can choose what data should be replicated?
Yes, very good question. This is a very common problem that you're raising here, and that's why we have a specific implementation for that we call event replication filters, and that allows you to be very selective of the events that you actually replicate. It can be replicated to pairs for redundancy, but also replicating down to the cloud. One of the benefits of the cloud, or sort of one of the benefits of the edge, is that you can reduce the amount of data that you need to ship between different places. So ideally, you want to do as much of the processing local, and perhaps end up with the result, sort of folding it, so to speak, down to a result, and having that result being shipped down to the cloud instead of having this endless stream of data and shipping everything down to the cloud. And you can be very selective in how you implement these using the Akka programming model. So the developer has full control over this.
I haven't used that Akka Edge before, but it seems to be quite interesting solution. I'm going to verify how it works, so maybe we can discuss about that more deeply next time. So thank you, Jonas, for very nice discussion, and see you next time.
Thanks a lot for inviting me. I mean, a lot of good questions, and I enjoyed the conversation. So thanks for your interest and time. Thank you.